known to like check my answer and it's not the same in the back of the book.
I wouldn't always trust what's on the line. That's for sure. All right, other questions?
Weekend.
That was fine.
You watched the XFL.
I did watch the XFL, actually.
St. Louis Battlehawks.
I did watch the St. Louis Battlehawks.
Yeah.
The game was super cool.
Was that?
So I thought the game was super cool.
Yeah, it was. It was all right. I think my personal take is it's going to take a while for the offenses to start clicking. It's the new football league that just started this year. Yes. Oh.
We have homework this week.
Yeah, you'll have homework.
I'm gonna throw this eraser at you.
Who?
You.
Well, he's talking to me right now.
I think he's
because
talking.
I'm not his.
Yeah.
Oh. You're so funny.
I think he might be talking to you, but I wasn't really paying attention.
All right. So we can move on, right?
That's right. All right. So the first thing I want to show you is the box and whisker plot. Except I forgot my keypads. I'm going to have to do this the long way. Well, with the keyboard.
I saw that and I was like, what in the actual heck is this?
The box and whisker plot is a way to look at, it's a graphical way to look at the spread of the data, is the idea.
Dr. Joe, how much monetization did you get from YouTube last month?
None.
You're not getting paid by YouTube?
Why would I be getting paid by YouTube?
With a video and not thinking he's gonna keep
Dr. Joe, can
Yes.
you follow along, like on laptops?
Yeah, absolutely. Please follow along on the laptops if you have them. All right, so let me just show you how to do it on that 6.3-8, and then you don't have to worry about doing it on your paper for the homework. How's that sound?
What?
What?
6.3-8 is one that I assigned, right?
Yes.
And if I do the box and whisker plot for that, then you don't have to do it for your homework, is what I'm saying.
There's two. There's two that you have to do.
Yeah, you're going to do it exactly the same. I mean, it's going to be one step on here.
Do I get extra
Yeah.
credit for doing it though?
No.
Why would I give you extra credit, Grace?
Because you like me? You can say you don't, but we all know it's true.
That's funny.
Haley's scared about your favorite position. She thinks that's okay.
Why would Haley think she's my favorite?
She can't grade papers correctly. She doesn't get the pay for it.
I was working on it last night. She goes, why did Michael think I graded his paper wrong?
Because she did.
She goes, oh shit.
Jerk. She can't pay attention
It's
to
too bad that Haley won't watch the video because she won't hear me making fun of her while,
She doesn't care.
No, I know she didn't care. If she cared, I wouldn't do it.
Oh yeah, I told you I cared when you made fun of me.
You don't care.
See, if I said it, he really wouldn't care. He would just keep doing it.
I don't know what you're talking about. All right, so that should be the right data for that one, if I typed it incorrectly.
Looks right.
Or typed it incorrectly. One of the two.
This is what number?
This is 6.3-8 on page 300. So here's how you do the box and whisker plot part. So the easiest way to do it is just to highlight all the data and go to Insert, and up here for the charts, let's see, let's do all charts because it has recommended charts. So this is going to do a scatter plot. Down here it says box and whisker.
Oh.
There we go. Now, Excel does their boxes and whiskers vertically, at least when it first puts it in there. But here's the idea behind it. So the way it calculates the box and whisker on Excel might be a little bit different than the way you learned it if you know how to do box and whisker plots. So the way it does it in Excel, if I'm correct, so the middle line here is your median of the data set. It's just easier for me to point there instead of my big fat finger.
It's still fun.
These two numbers here are the upper and lower quartiles. So the 75, the 75th percentile, the 25th percentile, the ones that are on the box. If you've done these before, you've probably drawn them horizontally versus vertically. But Yeah, well, Excel doesn't vertically, so. Now, if you learned this slightly differently, then the way you get the whiskers is to go to the highest and lowest points to draw your whiskers. But there is another method to do it, which is to go to the next highest and the next lowest value above and below the quartile. That's what Excel does. So this is not the high value for this. Well, it is in this case. In general, it doesn't have to be the high value for the data. In general, it's the next one past the upper quartile. The reason for that is also, this one doesn't have any, but it will also put dots in there if there are outliers if there are outliers that are significantly above the median. It'll put dots in there for the outliers. So for example, let me see instead of having that 2 in there, let me change that 2. Oops. It's 2 to a 5. So the little x is the mean, so obviously that 5 skewed the mean significantly. You don't have to worry about that. So this dot is telling me that the 5 is an outlier. So it didn't draw the whisker all the way to the 5. Okay, so the whisker is going to the next highest above the 75th percentile. Yes, Sam?
Does it calculate as an outlier, like above standard?
So there's something called the interquartile range. So the difference between your upper and lower quartiles. Anything that's between 1.5 and 3 interquartile ranges away from the median is a potential outlier, and anything that's 3 or more interquartile ranges away is an actual outlier. So all the interquartile ranges is this little distance between the two quartiles. That's all we mean by interquartile range. The way it determines these dots is by looking at, if you did say 1.5, so like right there would be 1.5 interquartile ranges. Right there, right? If I go above here, and go interquartile range, an interquartile range and a little bit more, that's definitely more than 1.5 above that. So that's when it's going to start putting in dots in there to specify potential outliers. Depending on when you learned box and whisker plots, if you learned them, you may or may not have done that. Did you do that? Did you do that? Good. Did you do that? Okay. Well, then why are you all looking at me like I'm nuts?
Because that's not how.
What would you have done?
Yeah, because what's the x-axis supposed to be?
The x-axis isn't anything. It's like your y-axis isn't anything. You draw them horizontally. It's just turn your head.
What'd you learn this in? AP stats.
Yeah.
High school? Okay.
You're gonna catch it.
It's just, so your median, for the first data set, the median is 2.5. So that's what that middle line is. And then this is the 75th percentile. That's the 25th percentile.
Bro, you keep throwing stats.
And then the 2 are the ends of the data.
It depends on how it should be the next. It should be the next data point above the 75th percentile, so not the last one. It depends on how it's calculated. In this case, it looks like it's the last one. I don't know why it's calculated that way.
Because like the lowest one is like 1.36, but the 1.36 is not there.
You know, you think you're good.
It might be doing it to the last. What it might be doing is drawing it to the last thing that's not an outlier.
So then, if you do them on Excel for like 6.36, do you just like print off?
Yeah, you can just print it out. Yeah, that's fine. You just print it. All right. So the whole idea behind why you might want to see a box and whisker plot. Again, the box and whisker plot here is an idea of how the data are spread out for the distribution. Looking at the box and whisker plot, does it look like there is any intersection in the distribution here? No. So it looks like this entire distribution is significantly above this entire distribution, right? Meaning, what do you think is going to be true about the means, especially if you look at the x's? What do you think is going to be true about the means? They should be different, right? I don't see 0 in the confidence interval. That's the idea behind the box and Whisker plot for this particular example, is to see graphically that, hey, there really isn't any distribution. I don't expect the means to overlap. I don't expect I wouldn't necessarily expect a different sample to generate a box plot that has the means flipped. That's the idea.
Alright, do the pool variance.
Would I do the pooled variance?
I just don't understand why I'm doing
Maybe
I'm
math
just
has
stuck.
just been here.
Oops.
I haven't been able to do that.
All right, so there's that variance.
Did you just press enter to get that in there? How did you get it in there?
Tab.
Yeah. Oh.
Mhm. Enter will just say it'll just screw it up. Okay, so there's the two variances, yes?
Yeah.
Okay.
Like that.
And so I just need to do 10 times that one plus, oops.
Why is it 10 times?
Oh, it's 9. Yep. Sorry. What are you doing, creeper? And then divide it by 18. Yeah?
That's what I thought.
That's pool variance? Is that what you got?
The pool variance or the...
That's the pooled variance.
No, that's not what it's supposed to be. Oh wait, can you square root it?
Like, well, I did it right, and then
That's exactly what I did. I don't understand.
I don't think that's exactly what you
must not have been exactly what you did, or you
Well,
would
I
have got
didn't do
that.
it on Excel, I did it on my calculator, but the calculation that you just did is the exact same thing that I did that I deducted.
I don't know what to tell you.
So you just did 9 times one variance minus 9 times the other variance.
Plus.
That's probably.
That is wrong in my notes, so that is definitely.
Well, that would do it. All right. Well, at least then it's not the other issue. All right, so
Not sure what exciting topic we're doing about
I
today.
guess you're math.
confidence intervals for variances.
One.
It's very exciting. It's not like we haven't already done it too. So, all right. Anyway, let's talk a little bit more about this. What we've been doing with the confidence intervals for the small samples. We do the pooled variances. Again, we use the pooled variance to try to get an estimate for the actual common variance for the two different two different populations. Right. That's the whole idea for doing the pooled variance. However, if you suspect that the variances are not equal, then that pooled variance probably isn't the best way to estimate. So they talk about this, and I'm not going to go through a bunch of this stuff in the book because this is more technical details than anything else. But they talk about it in the book. If you look at, it starts on page 295. Where at about the middle of the page, where it says, it is interesting to consider the two sample T in more detail. They go through and talk about what happens if you don't assume a common variance. And what's interesting is your variance term that's in the denominator, that's usually sigma or s squared over the sample size for x, and then the s squared over the sample size for y. If you're to have the large samples, the sample sizes get flipped in the denominators. So what I mean is that if you have the large samples, if you've got the large samples where we had the x bar minus y bar minus the difference of x and y's means, if this is your large sample, would they use n for x and m for y? All right. If you don't have the assumption that the two variances are equal, what happens if you go through and do all of the different simplification to get your t distribution? What happens is that these two denominators end up flipping, which is just weird, right? Because when you do, the reason why that's weird is because we know from the central limit theorem that the variance for x bar and the variance for y bar is approximated by these two expressions, right? Okay, not with the sample sizes flipped. So the whole point of this is that using the pooled variance idea, if you've got small samples but unequal variances, doesn't work very well. So if you've got if you suspect that you've got unequal variances, then you need to use, without these flipped, you need to use this expression like you do for the large sample, rather than the pooled variance idea. Okay. And the reason for that is that you don't want to try to treat these as equal, but you don't want to just go through and the idea behind that is that pooled variances pull these sample sizes in the wrong spot. Yeah,
So you flip them one?
you don't flip them at all. I'm saying that if you don't assume that they're equal, and you go through the pooled variances and simplify, they end up it ends up looking like this and getting flipped.
So you have to assume that m and n are equal?
To get the pool variance idea, we assume the variances are equal. The only way it would be right is if the m and the n were equal, which is why we don't ever do the flipping. So if you have, even if it's small sample, if you suspect the variances aren't equal, you would use the regular old denominator that you use for large sample. Right? This looks, without what I have circled in red here, this is the denominator for the large sample, right? Right? So if you have small sample but are guessing that the variances are not equal, then you're going to go back to this denominator rather than using the pooled variance example, is what that says. I'm not going to make you make that decision on a test. I'm just saying that in general it can happen. That was one of the things I was mentioning, if that was the case in the last one, but it assumed a common variance in that problem. When you said you had the wrong answer, that was one of the things I thought might have been causing the issue. Yeah, Sam?
When you're assuming the variances are equal, are you assuming they're exactly equal, or
You're assuming that the underlying population variances are equal, yes, exactly equal.
so like 10.2 and 10.1? That would be like considered different.
Yes. Yes, they would. Now, they're close enough that it's not going to matter when you're doing the confidence intervals in practice, but yeah, you're assuming that those would be different then. But what we're worried about is significantly different.
Like how?
One of the variances is 10 and the other one's 250. That would be significantly
What
different.
if it was like 10 and 100?
Well, then that would depend on your sample sizes.
Well, so it's-
We're going to talk about how we're going to talk a little bit today about how we can discern this.
Okay, great. Wait, that's what we use when.
You use the same as your large sample for small sample if you suspect that the variances are unequal. You use the same formula for a large sample as you do you use the same formula for the small sample as you do for the large sample if the variances are assumed to be unequal. You use the same.
Then you switch them.
No, you don't switch them. We don't want to switch them.
So why is the error then?
I'm saying that the whole point of the if they are unequal and you go through the simplification process, the denominators do get flipped, and you don't want that because it doesn't give you an approximation for the variance of the underlying distribution of the means. It's not the right approximation for the underlying distribution of the means because you're dividing by the wrong sample size. So you don't want to use that. That's the whole point. It's bad to use it if you suspect that the variances are unequal because it gives you the wrong approximation for the variance of the population. That's the idea. This is a lot more than I wanted to talk about it because I'm not going to have to do it.
It's not going to be on the test?
It's not going to be on the test, no. But it's something that you might come in practice if you're doing some sort of a statistical analysis. It is something that might pop up.
Okay, I appreciate the knowledge. Thank
I mean, there's more to learning in the class than just what's on the test. I know, isn't that crazy? All right.
You teach your algebra 1 students about commutative ring theory.
Why would I do that? That'd be crazy. I don't need to. It's like I had a colleague back when I was at a previous job that said it's like trying to teach a pig to sing. Frustrates you and annoys the pig. Why would I do that? All right. Okay, so there's also another idea with the degrees of freedom that I'm not going to make you do because the formula is absolutely ugly. But it might also pop up at a problem if you're looking at things and while your answers are slightly off. So we've just computed the degrees of freedom for small samples by adding the two sample sizes and subtracting 2, right? N plus m minus 2 to get your t value. There's another way to go through and figure out the degrees of freedom if you've got things that are not particularly close to normal. If it's symmetric but not necessarily close to normal to start with, you might have a little bit issues with your degrees of freedom if you're using small sample sizes. So there is a formula made up by a mathematician named Welch who went through and proved about the degrees of freedom, but here's why I'm not going to make you do it. All right, so the formula is, I don't know, I still have that in red. Here's what the formula looks. This R is representing the degrees of freedom that you would use. Here's how you would calculate it, and this is why I'm not going to make you do it. You don't have to write it down, no. It's in the book. It's on page 295, sorry. And I'm not done. Yeah, isn't that fun? All right, so this turns out that should be less than n plus m minus 2. And it turns out it typically reduces it significantly more than the n plus m minus 2 degrees of freedom. Think about what this does. The fewer degrees of freedom, what happens to your t? Does it get more spread out or less spread out? More spread out, right? Right? It's not as tall, it's wider, right? Like just look at your t table. If I flip over to t table here, I think I have that on here, don't I? There it is. What's that?
It's in there now.
The t table is a normal distribution, isn't it? That one I did. Notice that the numbers nearer the top are bigger than the numbers nearer the bottom. So that's telling us that the tails are farther out, right? Okay? So the fewer degrees of freedom you have, the wider the distribution is. Which means the wider your confidence interval is, meaning you're less confident, right? If you will. Okay? All right? So that's the whole idea with the degrees of freedom. That particular formula that I just wrote down that I don't expect you to know, I'm not going to make you do it. This reduces your degrees of freedom. Now, of course, here's another complication. This isn't always an integer. So you do what's referred to as the floor, or the greatest integer of R. The floor is just drop off the decimal. So if it came out to be 6.8, you would make it 6. Floor it? Yeah. Okay. So that in certain scenarios, you would want to use this for your degrees of freedom rather than the n plus n minus 2. I'm not going to make you do that. I'm just mentioning that this does pop up. Which is another thing that I thought that might have been going on. Yes?
So since this, it reduces the degrees of freedom?
Yep.
So that would give you a bigger confidence interval?
It gives you a wider confidence interval, meaning that you're less sure of where the mean is.
Okay.
Because being between 3 and 5 is better than being between 1 and 7.
Right.
That's the idea. All right. Enough of that, because I really didn't want to spend that much time on that. All right. Because I wasn't going to do it. I did want to talk about it because it's important to know that these things exist for later. But for our purposes, we're not going to do that. All right. So let's talk about 6.4. which is confidence intervals for variances. But we've already done things like this already. That was just disguised in problems. Remember the problems we had for that we asked you to find the A and B, so that A less than or equal to S squared less than or equal to B had a probability of equal to 0.9? Yes, it's the same thing, right? So same idea here. If you have your S squared, then what kind of distribution does this have? Thank you. Good. All right. So again, we're trying to find a confidence interval for sigma squared. But it's the same principles as what we've done for confidence intervals. I want to pin the sigma squared in between two constants so that I'm 90% confident, 95% confident, what have you, that the sigma squared is in between those two values, right? So we want the probability, if I want to find this A and this B, same concept as we did for confidence intervals for mean, means we want to make sure that the variable that we're interested in is in between the two numbers. That probability is actually equal to the 1 minus alpha. So the probability that you're landing in the tails is small. Now, if you go through and solve and rearrange this to solve this for sigma, or sigma squared, have the sigma squared in the middle. I'm not going to go through all the algebra. You should get n minus 1 s squared over b and n minus 1 s squared over a. And yes, the a's and the b's flip sides. Now, remember, where are we getting these a's and the a and the b from? Well, you told me that this has a chi-squared distribution, right? So this a and this b are going to depend on what you want for your bounds for your tail. So remember again that your chi-squared distribution, the graph, looks something like that, right? Yeah? Okay. So both your A and your B values here, you have to find both of them, as opposed to what we did with the means. When we had the T or the Z, we found one, we had a symmetric distribution, we got the other one for free. That doesn't happen here. We actually have to find two, because we don't have a symmetric distribution anymore. Yeah, Megan.
So it's not like a bell curve?
No, no, it's wonky. Yep. Yep. This part here by 0 is actually flat, and then it goes up to a hill, and then has that horizontal asymptote. But it's the same concept. We're going to find the two values. We want the probability that you're in these tails to be alpha, right? Same concept. So this one will have, this area will be alpha over 2, because we're going to do as symmetric as we can. Alpha over 2 probability that you're way above, or an alpha over 2 probability that you're way below. What? Sorry, go ahead.
It's not symmetric.
We're still trying to split our probability into two pieces, because beforehand we don't know if we're too low or too high. Okay, so this represents that the variance that we got was too low. It's outside, it's below what we thought. This is representing that it's above what we thought. So just giving us on either side. All right, so this one, if I remember the notation correctly, remember the subscript is opposite. So the subscripts that we had for the chi-squared values were the complement of the probabilities. Right, so this one, this value, if this is your A, this would be in the table what is chi squared sub 1 minus alpha over 2, then minus 1. It's backward of what you would think it is, right? So if alpha is 0.05, alpha over 2 would be 0.025. So you're looking for the chi-square sub 0.975. That the subscript is talking about the probability that you're above that value as opposed to below. It's weird, I know.
Why is it? So if it was
No, A is A. That's this actual X value here. That's really an A. It's the A that's going to go in here.
So if it was B, would it be 0.025?
Mm-hmm. Yeah. So the B value is. It doesn't matter. The A is the smaller, the B is the bigger. That's really the important part. Because notice how they got flipped in the probabilities, but you want to divide the left number by the bigger number to make it the smaller fraction. Right? The one on the left has to be smaller than the one on the right to be an interval. So I really do want to be the bigger number there. All right, so let's do an example, and hopefully this becomes a little bit more clear what we're doing. We can do this. Let's do it on. Why not do it in Excel? Because I think that's more fun anyway. So that way I don't have to actually look it up in the table. All right, so this is 6.4-2. Oh, you should have told me to zoom in on this. I forgot. All right, so I need a keyboard. Otherwise, it's really hard to enter values. All right. So there's only 9 numbers in this one, which is why I picked this one. 21.5, 18.95.
What is X's?
It doesn't matter in this case because there's only one population right now. Because all we're trying to do is get a confidence interval for the population variance. Here in a second, we'll have 2 population variances that we'll want to.
What number is this?
This is 6.4-2. Mm-hmm. And 23.1. All right. So if we're going to get a confidence interval for the variance, the first thing I need to do is get the sample variance. So this is the same way we calculate the sample variance that we did before, right? Use the var.s command. All right, so that's the variance. That's the sample variance. Oops.
Very active.
Very active. That's kind of funny. All right. So the other piece of information that we need to know are your chi-squared values. So this problem asks us to construct a 95% confidence interval. Actually, it says to do it for the standard deviation, but we're going to do it for the variance first, because what do you think you need to do if you're going to find this confidence interval for the standard deviation? What do you think you'll do? Take the square root, yeah. So, all right. So for the 95% confidence interval, the chi-squared values that we need. All right. So I need the inverse. I need one of these two. So this one would be your up to your from 0 up until the point that you're interested in. This one is from the point onward. So the RT is right tail. Okay. All right. So if we want 95% confidence interval. If we want the 95% confidence interval, the probability here would be 0.025 on the left side, right? And degrees of freedom here is 8, because it's n minus 1. Well, there's 9 things in the sample, so there's the 2.179, and if you check it out in the book, you should get the same answer in the table. So if I go to 8 degrees of freedom in the 0.025 column, I get 2.180, which is that rounded. Okay. The other one we need is the right tail. It doesn't matter. You can use the left tail and use 0.975, or use the right tail and use 0.025. Just make sure you use the right number. The right tail refers to probability above the number. The left tail is probability below the number. Okay, so for the bigger of the two numbers, you can use either of the two commands. You'll get the same value. Just remember that this is a left tail. So if you want the right number using the left tail, you got to go up to 1 minus the alpha over 2. You would use 0.975. If you use right tail, that's probability above the bigger number, you would use the 0.025. Either one works, you'll get the same number.
The 0.025 is it alpha over 2?
Is alpha over 2, yeah. So if I do this one, it's 0.975 and 8 degrees of freedom. Just to show you that you really do get the same number either way. If I do the right tail and do 0.025 and do 8, I get the same number.
Is that B?
That's B, yes.
Who's the first one?
The first one's A. Yep. This is your A. This is your B.
So why did you have to do 1 minus it for A? Like, there.
What? I did do 1 minus. No, the subscript, I'm sorry. The subscript refers to the probability that you're above. That's all the subscript is. It's just the way it's written. The way they write the subscript for the chi-squared, that 1 minus alpha over 2, that's saying that the probability that's above that A value is 1 minus alpha over 2. It's a goofy subscript, I agree. I think it's weird.
So the reason that they're different is the 0.025 is like on the one side, and the 975 is on the other side.
Mm-hmm. Yeah. One of the reasons why they did the subscript that way is because later on we'll be doing hypothesis testing, and we're looking for what are called for critical values, and you want to reject when you're above a certain value, so you look at that particular value for that. That's why they've got it written that way. All right. Are we okay with how I got those two values? Okay. All right, so then for your left, so to get your confidence interval then, I need to do 8 times your sample variance divided by the bigger number that gives you your left endpoint. Okay. Because remember, with n minus 1 s squared over b for the left one, right?
So you're doing 8 times b over
8 times sample variance over b. And then the other right one will be 8 times sample variance over a. Good news is if you screw up and put the wrong one in the denominator, you're going to know the lower number needs to be the left endpoint and the bigger number needs to be the right endpoint, right? I hope. This one okay? You suppose? Notice that this confidence interval isn't exceptionally helpful with the small variance cases. What does it tell you? You're confident. Your 95% confidence in the variance is somewhere between 1.58-ish and 12.68-ish. Okay. That's not great. Now, if I wanted the confidence, this is for the variance, right? The problem actually asks for the standard deviation. And you already told me what I need to do for the standard deviation, right? Just take the square root of both endpoints. Which is a little bit closer. A little bit better.
Tad better.
Questions on that?
You go back to the formula.
Which one?
So A plus N,
This one?
like the formula itself.
Oh, you mean the go back to Notepad?
Yeah.
Or OneNote, or whatever the heck it's called? That? There you go.
Scroll up.
Do we write the answer?
Oops.
Oh, Joe.
Okay, so,
Write your answer as an interval, like we did in the previous sections.
so why does it flip?
Why does it flip?
Yeah.
You have to reciprocate to get the sigma squared on top, but when you reciprocate, it flips the inequality.
Okay.
Right, so that's why. All right. Yeah, that's why we throw it over there.
It's the wall.
All right. So is this okay with figuring out those values? Not too bad. Okay. All right. So one of the things that we've talked about is that assumption that the population variances are equal, right? So one of the things that we might want to construct is a confidence interval that helps us determine whether or not we really can make the assumption that the population variances are equal. So what we can construct is a confidence interval for a ratio of the variances. If they're supposed to be equal, then what should be in the middle of your confidence interval somewhere if they're going to be equal? 1 should be in there, right? Okay. So ratio of variances, well, if we're going to do a random variable that's a ratio representing variances, I need a ratio of chi-squared distributions, right? What distributions did we talk about for about 2 minutes? Hasn't been very long. But it's a ratio of chi-squared distributions. That's the F, right? So the F distribution is a chi-squared over its degrees of freedom divided by a chi-squared over its degrees of freedom. Today is the 10th. All right. So, yes. What's the PDF? Nasty. I'm not writing it down. It's in the book if you want to go find it. I don't know what it is. But, so there's got a ratio of chi-squared distributions, and it's going to be gross. It's going to have gamma functions in it, for instance. I don't know what it is off the top of my head. All right. So if you look at the ratio of these things, we know that if we say we have n is the sample size for x, and m is the sample size for y. And I think the book has it the other way around. That's okay. Yeah, I know. Oops. Oh, it stopped. Okay. So we've got chi-squared of n minus 1 on top and chi-squared of m minus 1 on bottom, right?
Yes.
Okay. So I forgot to do something else. I forgot to divide by its degrees of freedom, right? So I need to divide it by n minus 1 there, divided by m minus 1 there.
The whole thing.
Yeah, well, on top the whole thing and on bottom the whole thing, right? So what's going to happen with the n minus 1s and the m minus 1s? They go away, right? So we'll just get sx squared over sigma x squared over sy squared over sigma y squared. They're variances. So right. No, those aren't squared. Because we need the n minus 1 on the front to make a chi-squared, and we're dividing by its degrees of freedom. So the n minus 1s will cancel.
Did the n minus 1 and n minus 1 cancel each other out on the fraction?
Yeah. Yep. All right. So we want to make sure that this probability is in between two values now. Sigma. It's okay. My handwriting sucks. We know that. All right. So if we play around with this now and get our values that we want. Let's see here. I would need to, I've got this, I think I got it written upside down from what's in the book. So I would have your A, and it would be multiplied by your SY squared and divided by the SX squared. And this will be your sigma Y squared over sigma X squared. And this would be your B times the Y squared over SX squared. This is an S. This is what the form would look like. These numbers, this A and this B, come from the F distribution like they came from the chi-squared distribution in the previous example, right? Right? We agree? So, since I'm out of time, I'll talk about next time where we get those values from, how we get those values from the table. Because notice in this case we need 2 degrees of freedom as opposed to just 1. So don't worry about 14 for the homework, since we haven't got to that yet.
Yes.
We'll just put it on the next one. Oh.
No fun.
Sorry.
I think so.
No, we should. No.